I'm Valerie George, and today I'm going to teach you a quick crash course on the science of hair color. A big disclaimer, I am not a licensed cosmetologist. In fact, I have a history of not being able to do my hair. Pretty much every school photo looks like this of me. Everything I'm going to teach you today comes from the viewpoint as a hair color chemist and my expertise in my decade-plus career formulating hair coloring products. Also, don't forget this PowerPoint presentation does contain copyrighted material, so please don't copy, borrow, distribute, or disseminate without the written consent of me, the presenter. Maybe you follow me on Instagram at cosmetic_chemist, or you know me from the Beauty Brains podcast, but most of my career was spent at Paul Mitchell, where I was not only the hair color chemist, but eventually their executive vice president of R&D. I think this has given me a unique perspective as a chemist, but also a unique perspective with salon professionals as I understand what they're going through in the salon. Everything I'm going to speak to you today keeps this salon professional perspective in mind, as well as the consumer perspective. We're not going to spend much time today speaking about hair structure because many of our other great presenters have talked about that, and also this presentation, due to time constraints, assumes you have this knowledge. But we're going to talk about things in the hair structure as it relates to hair lightening, the hair lightening process, because believe it or not, it is the first step in hair coloring, the types of hair colorants, and the products they go into. As far as hair structure goes, some of the things you have to keep in mind for today's presentation are the types of bonds we find within the keratin structure of hair. The most important bond when it comes to hair strength is this disulfide bond. If you're in the hair industry, you know that. This disulfide bond is a covalent bond. It's the strongest type of bond that we can find, and in hair, it's responsible for the structural integrity of the hair. When that disulfide bond goes away, the hair strength goes away. While it is a very strong bond, it unfortunately is also extremely sensitive to oxidizers and reducers, like things we would find in hair lightening or hair coloring, and even perming, and so this bond can go away with reactive chemistry. The other two types of bonds that hold the hair together are these salt bridges, which is an electrostatic bond that decreases when the hair is wet. You can remember that because salt dissolves when you put it in water. This salt bridge or electrostatic interaction will go away when you put it in water. When the water goes away, this bond will come back. We also have hydrogen bonding, which is the most numerous type of bond in hair. These also disappear when the hair is wet, and it's also responsible for the swelling of the hair. If keratin, hair's protein, is the most important molecule for hair structure, melanin is the most important molecule for natural hair color of the fiber. Melanin is found within the cortex of the hair, which is the center of the hair. It can be found in the cuticle, but it's extremely rare. In fact, the cuticle is primarily colorless, so you have to go into the cortex to see any color for the hair. Melanin is an insoluble polymeric pigment that's produced by melanocytes within the scalp, and as your hair grows, these melanocytes produce pigment up into the hair fiber. When I say polymeric pigment, I mean pigment because it's not soluble in anything, and it's actually a polymer. It's made up of repeating units, which we can see here in eumelanin on the left and here in pheomelanin on the right. Eumelanin and pheomelanin are the two primary types of melanin found within our hair fiber, but there are more types of melanin. They're just not commonly found or discussed. These are the primary ones. Eumelanin exists as a granular pigment within the hair fiber, and it varies in size. It lives between the different fibrils within the hair as little chocolate chips, and it's covered by a soft protein skin. How big the granule is and how much melanin is packed inside and the density of the granules to each other is responsible for determining how dark or how dense pigment appears in the hair. Eumelanin is responsible for black to very dark red colors. Pheomelanin, on the other hand, is similar in structure, but it has some differences. We see this sulfur group right here. And this allows it to have a little bit of a different color in hair. Pheomelanin is responsible for the yellowish to red color that we see in the hair fiber. It's synthesized similarly as eumelanin by the melanocytes, but there are some structural differences, and it packs into the hair and is distributed a little bit differently within the hair fiber. This sulfur group allows lots of stability for pheomelanin in the hair fiber. And in fact, if you've ever tried to lighten hair or bleach your own hair, you'll notice that the dark color that eumelanin offers goes away pretty quickly, and you're left with this stubborn reddish yellow orangeness, which would be the pheomelanin. It's just very stable. Here's an actual picture to show you what these melanin granules would look like. Here we can see the layers of the cuticle in this SEM photograph, and we can see these dark blobs within the hair fiber. These are actually melanin granules, likely eumelanin granules due to their shape. And so we can see that it's not evenly distributed throughout the hair fiber, but exists in these little chocolate chip types throughout the cortex. If someone has more pheomelanin than eumelanin, they would have reddish hair color. If they have more eumelanin than pheomelanin, they would have brown to black hair color. It's important to note that almost all hair types have, with the exception of albinos, have both of these pigments present. It's just the ratios and the quantities that determine the hair color. We've talked briefly about the biology of hair, and you've learned about it from some of the other presenters, but I do want to talk about the chemistry of hair. People say hair is biologically dead, but it's actually, yes, it is. It's chemically alive. And as a chemist, we take advantage of this chemistry, of these bonds on the hair fiber to get our hair coloring products to work. When we have hair growing out of our head, it's exposed to a lot of environmental stressors like water, ultraviolet light, oxidation, which could be from ambient oxygen in the atmosphere, or even applying different products on our hair like hair color. These will change these charges on the hair surface and manipulate hair's pH. Hair color chemistry takes advantage of this. So for example, if you have a really low pH on the hair fiber because you've applied low pH products, these charges will exist as positive charges, and we'll use that to our advantage. As the pH of the hair increases and goes up, these cationic charges are going to disappear, and you're going to be left with an excess of negative charges. Hair color chemistry takes advantage of that and uses those negative charges to stick positive dye molecules to the hair fiber. The first step in hair coloring or hair lightening is to actually remove your natural pigment from the hair, and that process is hair lightening. Consumers may do it to go platinum blonde. Maybe they want a lighter look, maybe they want highlights, or you need to prepare the hair for application for a dye preparation. In this case, with these two individuals, we have to completely remove hair's natural pigment to deposit this artificial, fun-looking color. But hair lightening also occurs when you're coloring your hair naturally. So when we're lightening hair, we actually have to do this first step, removing the pigment, and that means breaking down these melanin polymers within the hair fiber by chopping them up with different chemicals to get them to get smaller and wash them out of the hair. Don't forget, this pheomelanin is really stubborn. It's eventually going to lighten, but this eumelanin is going to go first. So how does the hair lightening process work? Hydrogen peroxide is the preferred ingredient. Now, I'm sure you know someone, maybe it was you, who found a bottle, that brown bottle of hydrogen peroxide under your bathroom sink, and you used it to give yourself some highlights, and the end result didn't look nice. Well, hydrogen peroxide has been used since about 1860 to lighten hair, so it's been used quite a long time. A British chemist and a London hairdresser created a lotion containing 3% hydrogen peroxide, which is a 10-volume solution, and they found it lightened the hair pretty well. Not only was their method very popular for the time, but it's still the basis of bleaching away existing pigment today. So they discovered something really great that works, and 160 years later, we're using it. Although today we're not using it alone unless you're using it as a sun-in or something to give yourself sneaky highlights, but we usually use it together today with ammonia or with persulfate salts in bleach or hair lightener. So how does it work? The exact mechanism is not agreed upon or clear, but hydrogen peroxide is an oxidizer. And we know that melanin is a polymer. Remember, I said it was a polymeric pigment. It's going to oxidize the polymer, break it down. The components become more soluble and eventually wash out of the hair. So this melanin molecule basically degrades. Melanin is stable in the presence of reducing agents, so like perms, for example, but it's not going to do well in situations where oxidation can occur. And hydrogen peroxide is just a really great oxidizer. When we are working with hydrogen peroxide, we're actually going to work with it in a developer solution. So it's not 100% hydrogen peroxide, it is a solution. And here are the common solutions that we find in the consumer and salon professional world. The percentage of hydrogen peroxide present in the solution is on the left. And in the United States, we typically speak to hydrogen peroxide in volumes, which is the number of liters of oxygen in gaseous form released. So we talk about it in volumes here, but these are the equivalents. And so it's purchased in a solution. It's generally a liquid or a cream, and the pH is very low, 2 to 3.5. Hydrogen peroxide is an active molecule, and when it's on the shelf in a bottle, we want to keep it inactive. And so we do that by keeping the pH very low of these solutions. When we deploy hydrogen peroxide, we want to raise the pH. Raising the pH is going to make it very active, and it's going to help decolorize that melanin in the hair. One thing I do want to note is a developer formula will typically have stabilizers present to keep the pH low, and it's also going to have chelating agents because hydrogen peroxide is very reactive to metals, either in solution or in the hair fiber. And so we don't want it to be reactive to those metals. We need to use a chelating agent. I mentioned that hydrogen peroxide is not super effective alone. Yes, we discovered it in the 1860s. We've been using it since then, but we've been slowly using it since then. And so in today's time, no one has 2 to 3 days for their hair to be weekly lightened. We need it to work very quickly. And the preferred vehicle for that is through adding hydrogen peroxide to bleach or hair lightener. We're going to use those terms interchangeably. We take this low pH hydrogen peroxide solution, add it to the alkaline pH lightener, and we're going to get this really fast lightening reaction on the hair. Bleach is typically a powder format, and the main ingredients are persulfates. These persulfates react with water, which is why it has to come in a powder format. And when it reacts with water, the persulfate is going to dissociate away from the counter ion and be ready to party with hydrogen peroxide and bleach melanin from the hair fiber. Notice the word ammonium here. That looks like the word ammonia. When the ammonium persulfate hits that water from the developer, it's going to release the persulfate and it's going to release free ammonia. So we're going to get an extra high pH party. When that 2 to 3.5 pH developer is mixed with lightener, we're actually going to get a final pH of 10 to 11. That's pretty high, and hydrogen peroxide loves to work at that pH level. When we're truly bleaching hair, like to really get it platinum, we want to use a 30 or 40 volume hydrogen peroxide. That's a 9 to 12% solution in order to really get the melanin deep down in the hair fiber removed from it. The application time does take 50 minutes. I know people want to move faster than that, but the reality is this bleach paste that you've created has to diffuse into the hair fiber, and you need time in order to do that. When we're employing a bleach or lightener, hair can be lifted up to 7 levels. And what I mean by this is hair is typically designated in a level system. So a black is a level 1, a platinum blonde may be a level 10 or 12, depending on who you're talking to. So theoretically, if you are a level 5, you can get to a level 12 using lightener. Notice I put my legal eagle hat on and I wrote up to 7 levels because I don't know if bleach can really do that, but we'll see. So the lightening process sounds pretty easy. We take this low pH hydrogen peroxide developer, we mix it with our bleach powder, it forms a paste, we put it on the hair, it decolorizes the melanin, we rinse it off, and all of a sudden we're walking out the door platinum blonde. That's great. Unfortunately, it's not as easy as that. You just don't leave the bleaching process at the door. In fact, you may walk out with a little bit more damage than you walked in with. And this is because when we apply these lightening mixtures on the hair, the molecules that we're using are not intelligent. They're not selective for the melanin. They're really looking for anything that they can react with. This includes hydrogen bonds, salt bridges, disulfide bonds, different amino acid groups, hydroxyl groups, polypeptide chains. Anything structural in the hair, they're going to react with. And so while you're decolorizing your hair, you're also damaging it, unfortunately. One way that we can tell the hair is damaged by the presence of cysteic acid. We're going to create these free acid groups on the hair, and this makes hair more porous. It means that it can absorb water more easily. One speaker I once listened to told me you can't wet a healthy hair because healthy hair is naturally hydrophobic. It hates water. When you bleach your hair, you increase the cysteic acid groups. That means increased water solubility. Or in the salon professional world, we say increased porosity. Hair is more porous. And so one of the negatives of porous hair is that things easily go in and out of the hair fiber. And one of those is color. So if you're lightening your hair and then coloring it afterwards, you'll get a lot of great color payoff, but that will fade out pretty quickly. Additionally, hair will feel like it's going to break. It's very difficult to comb. In fact, really over-lightened hair can feel gummy and stretchy because these disulfide bonds are being broken. And of course, damage is not uniform. The older the hair is on your head, it's been exposed to more environmental stressors, and subsequent lightening services or other damage means that the tips of your hair, the ends of it, are really damaged, and what's freshly out of your hair is not as damaged. And that lack of uniformity can be a really big problem when we're adding colorants to the hair. Speaking of colorants, now that we've lightened our hair, we're ready to add some pigment back into it. I never know how to arrange this section. Do we talk about the types of colorants used first? Do we talk about the types of products they're used? Do we mix it all up? And I've decided the best way to approach this is to talk about the types of colorants or molecules that we use in hair color, and then I'll walk you through the formulas that we use them in. The first type of colorant we would use in hair color is a pigment. Pigments are physical particles that are not soluble in anything. We often use the term pigment interchangeably with dye or colorant, but when we're referring to a true pigment, this is a physical item like makeup for hair. The color that you see is the color that you get. You can use synthetic pigments, which tend to be bright, have really great stability. They can be surface modified to be hydrophilic or hydrophobic, which can affect substantivity on the hair. And then we also have iron oxides, which are also used in color cosmetics. These can create brown, red, yellow, and other nude shades, like in a root touch-up spray. We don't really use these, so I'm not going to spend a whole lot of time on them. Acid dyes are different from pigments because they're soluble in something. They're actually soluble in water. And so, although we may use the term pigment and colorants interchangeably, these are truly actually dyes. We also call acid dyes direct dyes because we can directly see the color of the powder is going to translate to the hair. So you'll see this term as well. Acid dyes are very large in size. We can see that they have many, many molecules, much like melanin. This large size gives them a high molecular weight, and they also have a negative charge, although you can't see that within the photograph here. So these would be considered anionic. Acid dyes really stain, and unfortunately they don't only stain the hair, they do stain the skin. And in fact, they stain the skin more than hair because skin is more basic in charge than hair, so the dyes are preferentially binding there due to their anionic character. When we are working with acid dyes, the dyeing effect is a function of pH, and the pH works best between 2 to 4. Because of their size, they really just attach to the exterior of the hair. They can't penetrate very well. And so we have to swell the hair fiber and get these dyes to penetrate in. The good news is once they're in, they're difficult to get out unless you hate the color, and then that's bad news. The more you use these dyes, the more the color intensifies over time. You'll notice that we have Acid Violet 43 here and a purple shampoo. Acid Violet 43 is the acid dye that's responsible for that secret behind your salon professional's chair. Purple, although we're not going to get into color theory here, helps neutralize yellow tones in the hair and make hair appear more platinum than it really is. The more you would use a purple shampoo, the more you're going to get that color intensity. Basic dyes are also considered direct dyes, and they are not anionic or negatively charged in character, but they're positively charged in character, so opposite of acid dyes. They also are used at a different pH range of 4 to 9, which is a more natural pH for hair coloring products. They're not as bright or vivid necessarily as acid dyes, so basic dyes are really good for when you want natural hair coloring situations. They're very big molecules, so they have a high molecular weight. Again, they're not going to penetrate very far into the hair, but we don't need them to because they are positively charged, and for the most part, hair is almost always negatively charged due to its isoelectric point of 3.6. We are going to employ that chemistry to get it to stick to the hair fiber. Nitro dyes are the last category of direct dyes that we use, and nitro dyes are just that. They have to have a nitro group. They have no ionic charge. They're considered non-ionic, so we have to rely on their small size to penetrate into the hair fiber. They're just simply not going to attach to the outside. You'll notice all of these dyes have that nitro group in the molecule because that's the requirement to be nitro. Because they're non-ionic and they have no ionic charge, they generally have poor water solubility. So we really have to do some tricks as formulators to get them to penetrate into our dye solution. Again, because of their size, they're affinitive for hair. They're not affinitive for hair based on charge. Although these have a very simple molecular structure, they actually have a lot of variation in color. We can see that even though they both have this nitro ring here, these little different substituents really shift the color in different directions. For example, let's take HC Blue 2 and HC Yellow 2. Nitro dyes are primary yellows, reds, and orange, but we do have this blue dye right here, which is very structurally similar to the HC Yellow 2, except HC Blue 2 has this amine group pendant sticking off. This functional group alone shifts the dye away from this yellow and makes it a really beautiful, warm-looking blue. Likewise, with HC Yellow 2 and HC Yellow 4, the addition of this ethoxy chain right here shifts this yellow 2 dye from being a nice warm yellow to a really nice cool yellow. One last thing I love about nitro dyes is they don't really stain the skin. That's one of the other benefits to them. But also, one negative to using these is their size. We've talked about those advantages. They can go into the hair very easily because they're small, but they'll also fall out very easily. Oxidative dyes are the fun category of dyes, and we would consider these dyes to be permanent, and they're typically used in permanent and demi-permanent hair color. Oxidative dyes don't have this lightening effect themselves on the hair fiber, but the catch is they go in formulas that do have a lightening effect. Because oxidative dyes generally don't have a color, there's no intrinsic color to the powder, this means the color that you see is not the color you get. You actually have to react these dyes together and with an oxidizer, and oxidizer is required in order to form the color. In fact, 2 dyes are required to make 1 color, and we call these dyes bases or primaries, couplers or secondaries. These dyes are small on their own. We'll take a look at the molecular structure in a moment, but because they react together to make a bigger molecule, they're going to stay in the hair for quite a long time. So these dyes are very long lasting. Let's revisit my statement that oxidative dyes don't have an intrinsic color that imparts color itself to the hair. Here's a couple oxidative dyes for you to look at that are colorless. Okay, so the crystal has a little bit of color. We can see that this one's a light grayish purple. We can see that this one's a sparkly gold, a light orangey peach. This one's pretty white. This isn't the color that they impart to the hair fiber, although the lower left one would be pretty cool. This is just the natural color of the crystal. That doesn't mean it's going to do that for the hair. And so we have to react these together through oxidation with hydrogen peroxide, which is why they're called oxidative dyes, in order to get that color. Let's take a look at the molecular structure and how that occurs. As I mentioned, we have two categories of oxidative dyes called primaries or bases, or couplers or secondaries. We use those terms interchangeably. And in general, you need one base to react with one coupler to polymerize together to form the color. It's important to note these categories because we would never want to put two bases together or two couplers together. In fact, if you do that, you're not going to get a color to form. You have to have these combinations of two categories. The other reason that these molecules are not totally colored is they don't have a conjugated electron system. We have to create that through oxidation. If you remember the acid dyes, the basic dyes, the nitro dyes, they already have a conjugated electron system. Here they do not. We have a ring with the double bonds, but that's not the same as a conjugated electron system. So we're going to do that in just a moment. I'm going to walk you through the combinations that I would make with a coupler like meta-aminophenol with these two different bases. So we'll react meta-aminophenol with p-phenyldiamine. We'll react meta-aminophenol with this really long one I call WP5. And likewise, we'll do 4-amino-2-hydroxytoluene with PPD and WP5 and show you the different results that occur from that combination. So the first coupler we want to react with the two different primaries is meta-aminophenol. And if we react it with PPD, we can see that we've gone from a single molecule in a single molecule to a conjugated electron system. The end result is a very, very dark red color. It's so red it looks black. If I were to take meta-aminophenol and react it with a different primary, WP5, we're going to get a much smaller molecule, but as you can see, it's a conjugated electron system. This molecule, because it has different functional groups attached, is going to be a very beautiful, clear red. It's not going to be as dark as the meta-aminophenol and PPD combination. What happens if we take PPD and put it with 4-amino-2-hydroxytoluene? Are we going to get this darkest red black color? No, we're going to get a darkest orange black color. Just switching the coupler or secondary with the PPD, we still get a conjugated electron system, but the molecular structure is different. So we have a different structure showing up. Likewise, if we take this same coupler and combine it with WP5, we're going to get a really clear orange, not a really clear red. And so as a chemist, my job is to take these different oxidative dyes, combine them in different combinations with each other, and it's the combinations of combinations that make different shades. As you work with these different combinations of primaries and couplers, you get pretty familiar with what combinations can occur, although the base of the formula that you're using does have a huge impact, so it's not always a hard and fast rule. This is an example of a dye chart from a supplier which shows you all the different combinations that could be created. These are not finished hair color products. These are simply combinations of the individual primaries and couplers to give you an understanding of what color possibilities can be created. With oxidative colorants, we do need other ingredients. I've reiterated over and over, on their own, oxidative dyes don't have a color. We need to react them together for a color to form. And here are some of the other ingredients required in that chemical reaction. Let's go through them. We need an alkalizer. We have to create this high pH environment for hydrogen peroxide to be effective. Don't forget, when we have a hydrogen peroxide solution, it has a very low pH. It doesn't work at that low pH. And so we need to raise the pH for the hydrogen peroxide to work and oxidize the dyes together. We also need this high pH in order to swell the hair fiber. These molecules are very big. The reactions are happening very fast, and we have to not only get hydrogen peroxide in the hair to decolorize melanin and to assemble the oxidative dyes together, but we have to be able to get these huge dyes that are already formed in the hair fiber. And the alkalizer that we use to create this pH environment of 9 to 10.5 for hair color is ammonia, MEA, or aminopropanol. Ammonia is the most effective. It swells the hair at low levels, is very synergistic with hydrogen peroxide for accelerating the bleaching of melanin. They like to party together. The downside is ammonia smells. It is a gas, so we definitely notice when it's present. But the good thing is it's a gas, so it leaves the hair. It doesn't stay inside. It keeps the pH party high, does its job, gets the heck out of there. MEA is monoethanolamine. It's a liquid, so it doesn't smell. But unfortunately, it stays in the hair and reactivates continuously. It's very hard to get all the way out of the hair fiber. There was a May 2014 journal study that showed monoethanolamine use over use is as damaging or more damaging to hair compared to ammonia. A lot of people think monoethanolamine is more safe because you can't smell it, but it actually is worse for your hair, and it causes contact dermatitis. It's also way less efficient than ammonia, so you have to use several times the quantity, and you still don't get the same lightening effect because I guess it doesn't like to party as much with hydrogen peroxide as ammonia does. Aminopropanol is not really an alkalizer, but you can use it to swell the hair a little bit in demi-permanent hair color. Of course, we have to have hydrogen peroxide. As we mentioned, oxidative dyes require oxidation. You get that from an oxidizer like hydrogen peroxide. In hair color, we typically only find 5, 10, or 20 volume. The goal is not to bleach the hair, it's to lightly decolorize the existing melanin and deposit dyes into the hair fiber. Also, if you use more than 20 volume, you can actually end up oxidizing some of your dyes away, which is counterintuitive. We have to have an antioxidant. We need to protect dyes from oxidizing prematurely in the formula. We don't want the tube of hair color to react when it's on the shelf or in your back bar at a salon. We want it to react on the head, and so that means putting antioxidants into the product. Chelators. I mentioned in the lighteners section that heavy metals are horrible with hydrogen peroxide. They catalyze it like crazy, and so we need to remove metals from solution. And then, of course, we need hair. People always laugh when I say this, but you have to have hair to put these ingredients on. And in fact, if you were to mix a bowl of hair color together and mix it up, it would be very slow to react. You put a swatch of hair in it, boom, reacts very quickly. So now that we know the types of colorants, let's go through the types of products they go through. So temporary hair color is a category of hair color that's like makeup for hair. And if we know what molecule is responsible for makeup for hair, it's pigment. Remember, it's a physical particle that physically rests on the hair. And this formula has to be created in such a way that the dye molecules or pigment molecules only stick to the outside of the hair through electrostatic links. And so when we talk about temporary hair color, we're talking about absorption onto the hair fiber. Notice nothing is in the inside here. It's a temporary effect on the outside. Sometimes you can use acid and basic dyes. They do minimal staining, but sometimes you can get them to wash off pretty quickly if they're strictly on the outside of the hair. Typically, we would use a polymer to affix these to the outside. Semi-permanent hair color goes a little bit further than temporary. We have a tiny bit of molecules poking in here, but not too many because we're using basic dyes and acid dyes. And if you remember, these are very large molecules and they don't like to go inside the hair, so most of them stick on the outside of the hair through ionic interaction. Basic dyes being positively charged, acid dyes being negatively charged. Maybe it's the Nitro Dyes that have gone in here because they're so tiny. At any rate, semi-permanent hair color is typically vibrant, really fun hair color. And, you know, if you love the way the color looks, it won't last long enough. If you hate the way it looks, especially blue, it will last forever. And so for a multitude of reasons, semi-permanent hair color, longevity is a little hard to describe, but in general, semi-permanent hair color should last up to 4 to 6 washes, which we know is not the case. Demi-permanent hair color is generally considered to last up to 4 to 6 weeks. And this is because we get lots of absorption into the hair fiber as well as adsorption on. And this is because we're using all sorts of dyes here. We're using a little bit of oxidative color in addition to nitro dyes and basic dyes to give a really beautiful dimensional look. I love demi-permanent color because it takes advantage of the natural hair color that you have and enhances it with a little bit of a stained glass type look. Here is the Demi, which is a product line I formulated. So I love demi-permanent hair color. Because we have oxidative dyes, we have to have all of these other items present, which is why I listed them here. And perhaps you didn't notice additional ingredients in semi-permanent color or temporary hair color. That's because these ingredients have to be present for the oxidative dyes to work. Finally, we have permanent hair color. Permanent hair color uses strictly oxidative dyes. We rarely use other types of colorants within permanent hair color, although you can for a multitude of reasons, but we're primarily using oxidative dyes. And in permanent hair color, we want all of the dyes to penetrate. We want the hair color to last forever. So we want absorption as much as possible. Oxidative dyes are the ticket to that. And this is because you can use an alkalizer with them. Typically, we use ammonia. It's the best working one. You can use MEA. This is going to swell those hydrogen bonds in the hair and allow the color to penetrate and diffuse into the hair fiber. Of course, we have our other hero ingredients that make oxidative hair color work. We'll find those in the formula as well. You'll notice here I have a box of hair color that you would get at a mass market store and a tube of Salon Professional hair color. I'm very sorry to folks in the audience who work in the Salon Professional community and have been told that box hair color is horrible for hair. They use the exact same ingredients. It's the exact same chemistry. And the only difference that we would find is the way the shades are nuanced together, maybe the level of ammonia or MEA, maybe the level of hydrogen peroxide that's used. But from a chemical perspective, they're the exact same thing. I typically go over this in my soapbox section. We just don't have time for that today. But from a chemical perspective, a hair color that you would get in a box called box hair color is the same as a tube of Salon Professional hair color as a chemist putting them together. Speaking of soapbox, I would like to get one out and climb on it now. When it comes to hair color, there are many things that push my buttons, and we'll go through a couple of them today because we're running out of time. I wish I could go through all of them. My first soapbox topic is PPD. You may remember PPD from a few slides ago when I was showing you the reaction in which a primary reacts with a coupler. We reacted PPD with meta-aminophenol and PPD with 4-amino-2-hydroxytoluene. We formed that darkest red-brown and the darkest orange, respectively. That's what's great about PPD is you can use it in small quantities to form these really dark colors. When I was going through that reaction with you, I was very specific to mention that you always have to use a primary with a coupler. You would never want to use couplers alone because you won't get color, and you would never want to use primaries alone. You would never want to use a primary alone because a primary is so electron hungry, it's searching for these couplers in the molecule. And when it can't find any, it's going to say, well, I have to react with myself. And in the case of PPD, it's going to react with itself through this reaction to form a molecule called Bandrovsky's base. Bandrovsky's base is a very dangerous molecule. PPD itself isn't dangerous, Bandrovsky's base is. And unfortunately, people confuse the two. Bandrovsky's base is allergenic. It's what elicits that PPD allergy and also is genotoxic. People think PPD and Bandrovsky's base are carcinogenic. That's actually not the case. It's just allergenic and genotoxic. So when we're formulating with PPD or other primaries for that matter, it's very important we're using the appropriate amount of coupler with it. PPD gets a bad rap because of this, but there's other molecules that this happens to. They're just not as infamous. You may be wondering why PPD is an issue when we've been using it since 1862 or 1863. In fact, L'Oreal's been using it since 1909 in their hair color, and it's just now getting this really bad rap. What's going on with it? PPD and black henna tattoos, that's what's happening. On the right, we have a picture of a woman with light brown ink on her hands. This is the color that henna is supposed to be. Black henna is not brown. It's black like its name, and we can see it in the picture on the left. Black henna gets its color from PPD, not PPD safely coupled with another colorant. It's PPD that has coupled with itself to form Bendrovsky's base. There's an interesting paper from the Journal of Cosmetic Science, actually two papers from around 2015 by Dr. Catherine Cartwright-Jones, where she proposes that the latest PPD epidemic that we're having comes from the 1970s, where there's a rise in tourism to beach communities, and the beach communities where these black henna tattoos are being given. And it's creating this surge in people who have a PPD sensitivity. What's interesting is that you may get a black henna tattoo and not have anything happen the first time, but then you'll go get your hair colored after that and you have a severe allergic response, and you can only think of the hair color as to blame, when in reality the black henna tattoo may play a role. Black henna is illegal almost everywhere that you can think of, including the United States, and every summer, in fact, the FDA puts out warnings. I also put out a warning that if you see black henna, turn away. It's not allowed, and that is no matter where you go in the world. So the theory is black henna tattoos are responsible for the rise in PPD allergies despite its safe use since the 1800s. Natural hair color is a topic that really gets me going. Remember all those chemicals we talked about that are required for oxidative hair color to work? Well, they're not natural. In fact, most of them are synthetically derived. Most of them come from benzene chemistry, which is from the petroleum industry. And these are not natural items. So it really gets me when a brand implies their hair color is natural or henna-based, let's say, and they have a bunch of direct dyes stuffed into it that come from benzene chemistry. Or even salon brands saying, this hair color is healthier for your hair, healthier for you, because it's more natural. Well, at the end of the day, all of the hair color companies are using the exact same chemistry. And so when you imply something is natural, we've been trained for years to think that natural must be safer or better for us somehow, when the fact is we're really using the exact same chemistry as everyone else. I really just don't like that. The only natural hair color is henna. Henna is a natural colorant. Lawsone is the active ingredient. People can also use other plant compounds like indigo or chamomile to color the hair. You have to use combinations of them. They require a long time to penetrate into the hair fiber because the molecules are so large. Often the color palettes are unpredictable, they can be weak, and because they are plants, they can have lots of heavy metal contamination. And heavy metals are not good if you ever want to go back to coloring your hair another way. Also, there's often no way to remove these colorants from the hair, so you either have to cut the hair off to remove them. Even heavy bleaching won't work. However, there are a lot of merits to using henna-based hair color. You can get great results when you see someone experience with it, and many people do enjoy it, and it's been used for thousands of years, so there's something with that. And there you have it. That's hair color in a 1-hour nutshell. I hope you enjoyed this presentation. If you'd like the full 8-hour presentation, just let me know.